Welcome to our presentation, which is for our paper, Multimodal Differentiation of Obstacles in Repeated Adaptive Human-Computer Interactions. The authors are Felix Putze and Mazen Salous, and it's me, Mazen Salous, who is presenting these slides. Human-computer interactions are actually very dynamic. That means persistent or volatile interaction obstacles can impair a user's cognition or perception processes. We believe that a memory-based obstacle caused by a secondary task memory load can impair a user's cognition. If we look at the left side illustration figure, we see a human-computer interaction symbol, while in user's mind there is a secondary task memory load impairing her or his user performance because it causes a so-called memory-based obstacle with low free working memory capacity. This is an example of volatile obstacle, while an obstacle can be also persistent. For example, for the user's perception, if we have a user with color blindness, the visually presented items in red and green colors will be seen as brown variants, as we can see in the right side illustration figure, and this will cause a so-called visual obstacle and confused user behavior. And this is a persistent obstacle. Therefore, we need to automatically detect obstacles and accordingly adapt the user interface. Related works can be categorized in two main directions: customization and adaptation techniques. Both are aiming at improving the system's usability, while customization techniques grant users control to customize the user interface adaptation according to their specific needs. That means according to different interaction obstacles. Therefore, no obstacle detection is discussed here. And even in case of discussed obstacle detection, so visual obstacle detection of color blindness, as discussed by Kaiser and colleagues in 2017, it is a specific test, cannot be smoothly integrated in SIGCHI applications. Adaptation techniques are more related to our work. Adaptation techniques grant control to the adaptive system itself, which identifies users and adapts the user interface accordingly. However, in the state-of-the-art models, either no human cognitive modeling is discussed or solely user performance dependent is discussed with no behavior-based modeling and, more important, with no human perception and cognition modeling, because those human processes can be useful for a repetitive user interface adaptation in consecutive sessions with dynamic situations of volatile obstacles, for example, or wrongly decided user interface adaptations. Therefore, we introduce our model, which is dynamic repeated adaptive human-computer interactions. So we believe that multimodal data can be recorded. So concretely, brain activity data can be recorded to detect memory obstacles, and behavioral data by encoding user actions can be recorded to detect confused behavior caused by visual obstacles. And then both memory obstacle detector and visual obstacle detector can be integrated under an overarching probabilistic model to decide for the most suitable, most probable user interface adaptation for each session, because this can be dynamic in consecutive sessions. So how to validate and evaluate our model? We have to choose an SIGCHI application. We have chosen the matching pairs game as SIGCHI exemplary task because it can be a representative task for many other SIGCHI applications, because it involves multiple step operations, visual recognition, spatial and symbolic memory, working memory actions, and so on. We decided for a single player mode where a player is asked to find the pairs with as few rounds as possible, and we decided for a card for colors. That means our cards show colors, not pictures, because for pictures, we may have different user preferences. So users can recall some pictures easier than others and so on so we decided for a neutral stimuli with showing only colors. In the no obstacle game, only distinguishable colors will be shown. In the memory obstacle game, distinguishable colors also will be shown, but with a secondary task, which is cumulative sum. For each revealed card, a random number will be said, and the user should calculate the cumulative sum. This will impair his working memory as a memory obstacle. And for the visual obstacle game, we simulate the color blindness effect by showing only brown variants. We designed user interface adaptations for our obstacle. For the memory obstacle, our game will show previously seen cards for each non-matching revealed card. This will ease the task for the user. And for the visual obstacle, so the cards will be shown as brown variants, which is not easily detected, but we use auditory identifiers because hearing is not impaired and user can hear well, for example, A, B, C, and then our users can achieve the game and finish it easily by recognizing the positions of the cards based on the heard auditory identifiers. So for data collections, we need to collect data from all combinations between game variants and user interface adaptations. That means no obstacle game, memory obstacle game, and memory obstacle game with its correct user interface adaptation, and also visual obstacle game and visual obstacle game with its correct user interface adaptation. And also we need to collect data from obstacles with wrongly decided user interface adaptations, either for the case of wrongly decided adaptations, which should be corrected later by our cognitive model, or for the case of visual obstacle, which can disappear later and our model should react accordingly. Therefore, we need a set of obstacle detectors according to different user interface adaptations. As we can see in the right side figure, for no adapt, memory adapt, and visual adapt, we have different obstacle detectors. Those will be used by our model in subsequent sessions. And in the left side, we can see the four main parts of our architecture. Number one is a real photo from our experiment. Number two, the recorded behavioral data and behavior-based obstacle detector. Number three, the recorded brain activity data and the obstacle detector based on brain activity data. So behavior obstacle detector and brain activity based obstacle detector in 2 and 3 are integrated under the dynamic Bayesian network, which is depicted in number 4 to decide the suitable user interface adaptation in consecutive sessions. We expect that the EEG data, the brain activity data, will be good for detecting memory obstacles, and the behavioral data will be good for detecting visual obstacle detectors. So after evaluating all obstacle detectors from all combinations between user interface adaptations, no adapt, memory adapt, and visual adapt, and also behavioral and EEG data, we found that our expectation was correct. The EEG data in average was with the best accuracies for detecting memory obstacles, and the behavioral data for detecting visual obstacles. In this way, we have valid data streams, valid data distributions, which can be learned by our probabilistic repetitive user interface model, which is dynamic Bayesian network. It will learn from the first interaction. It can decide between no adapt or mem adapt or vis adapt with an accuracy of 72%, and it drastically improves in the second interaction to 98% because it improves and it learns from consecutive HCI sessions. As a detailed analysis in number 3, A and B, we trained also our dynamic Bayesian network for only wrong or only correct user interface adaptation decisions from the previous interaction to analyze and investigate how well can our model consolidate and correct the user interface, the wrongly decided user interface adaptation decisions. And we found that it can correct the wrongly decided user interface adaptation decisions. Finally, to summarize, we see that perception and cognition processes can be embedded during human-computer interaction with multimodal data. Multimodal obstacle detectors can detect those obstacles, and those obstacles can be obstacle detectors can be integrated by a probabilistic model to decide for the best suitable user interface adaptation in consecutive sessions to consolidate or to correct the user interface adaptation in subsequent sessions. Thank you very much for your listening. That was our presentation.